So, good evening, everyone, and welcome to this brand new lecture. And in this brand new lecture, we are going to do the old stuff. We were dealing with the problems of electrostatic potential and electrostatic potential difference, I guess. And we had seen a variety of problems where we had found out the potential due to different type of charge distribution, mainly the potential due to a ring. We had also seen the potential due to a disk, and we had also seen the type of problems that can come where you have charge moving, and we had to find out the kinetic energy or the velocity of the charge when it passes through the center of the ring or center of the two charges. Do we remember those questions? Yes or no? The important point to remember in any of those questions was we had to find out the potential difference between the 2 points. Once we find out the potential difference between the 2 points, we can find out the difference in potential energies, and then we can use either the work energy theorem or we can use the law of conservation of mechanical energy to solve the remaining question. The last configuration that we saw was the configuration of a ring, and in that ring, importantly, the charge was not distributed uniformly, it was distributed non-uniformly, but you must understand that potential due to a ring at any point on the axis of the ring does not depend on the distribution of charge. This is a very important thing that you must understand. Everyone knows this, yes or no? Well, then that takes us to the next type of charge distribution, and that is your favorite type of charge. You can call it as a conducting sphere or a conducting slash non-conducting sphere. So that is the next type of charge. So you will have, this is a conducting sphere, or you can have a hollow sphere which can be conducting as well as non-conducting. Now in this type of charge configuration, you have charge only coming on the outer surface. As you can see, charge is only on the outer surface, and then you will have to find out the electric field and electric potential at different points. And if you remember, we'll go through it very quickly. Outside the sphere, if we have any point which is outside the sphere, anyone remembers what was the electric field outside the sphere? We have done it so many times. Does anyone remember it? For any point outside the sphere, do we remember
Q
what
by
it
R
was?
square.
It was kq by r square. It was same as the electric field created by a point charge placed at the center. So we all remember that formula, that the electric field outside was kq by r square. We have seen the vector formula as well. Right now what we are concerned is the potential at any point outside, and again it is same, exactly same as the potential created by a point charge. So this formula outside the sphere does not change, it is same. If you remember the formula of a point charge, you should be able to remember this. No point in any further discussion, you will have to remember this formula no matter what. Now from outside the sphere, we now slowly move towards the sphere, and the first point that we encounter is the surface of the sphere. And what is the electric field on the surface of the sphere? We have also seen this formula, 1 by 4 pi epsilon naught, or kq by capital R square, where capital R is the radius of the sphere. Similarly, the potential on the surface of the sphere will be kq by capital R. Again, same. as the as the electric field and potential created by a point charge. What does change though is inside the sphere, because inside the sphere now you know, if you apply Gauss law, there is no charge coming inside the sphere. Since there is no charge, there is no flux, and hence there is no electric field. So the value of electric field by Gauss theorem also you can understand that the value of electric field at any point inside this sphere, since there is no charge, the electric field would be zero, and therefore your potential, remember, potential would be constant. So remember, electric field at any point inside is zero. So remains constant. V is not zero, it remains constant. So remember, V at any point inside will be equal to V on the surface, and V on the surface is kq by r. So it remains an equipotential thing. Inside the sphere, everything is of the same potential. Everything is on the same potential. Even the center of the sphere, the potential is also same as the surface of the sphere. Do we understand this? Yes or no? I hope everyone has noted this formula. Yes or no?
Yes.
Again, I am giving you both the formulas together because there is no time for me to come back and do any sort of revision of electrostatics. If we can do it even once, that would be a big achievement, and that is what we are trying to do. Everyone has noted this down, yes or no? Yes?
Wait for 1 minute.
Okay. Let me know once you're done. Let me know once you're done, beta. We are doing these things so many times, repeating them, because I know that a question is going to come from this in your exam. And if you missed something in the first attempt, some point in the first time that we wrote, you get a second chance to redeem yourself, because after this you might not get a chance. I will not get enough time to go through it once again. All the formulas are not possible for me to go before your JE. It's not possible for me to go back through the entire thing once again, right? So be very careful. One of these question is going to land up in your paper, beta. Okay, I'm sure about that. Let me know once you are done so that we can move ahead.
Done, sir.
Boys,
Done, sir.
done, sir. Then, sir, this very important diagram, sir, which is coming on your screen, sir. This is the diagram where you have the sphere and the distance on the sphere is given, and then the graph. We have drawn this graph many times. I know we have drawn the graph for electric field. Now, on the right hand side, you can also find, if I call graph number A as the graph of electric field, the graph number B is the graph of electric potential, and these graphs have come many times. The difference is electric field, as you can see, inside is zero, but the potential inside is definitely not zero. In fact, it is same as the potential on the surface, which is kq by r. So everything that you have written in alphabets and words and numbers. It is drawn in the form of a graph right in front of your eyes. I'll give you 2 minutes to draw this graph.
Done, sir.
Boys, boys have to come up as well. We may have drawn the graph of electric field earlier on, but now both the graphs are side by side, electric field as well as electric potential. And remember here, potential of one point is taken as zero, and that point is at infinity. Now remember, two cases at least we will see in which electric field electric potential at infinity cannot be taken as zero. So those two conditions are also coming up. Don't worry. But right now we are dealing with conducting sphere or conducting slash non-conducting shell. And I hope we have done the diagram and the graph. Let me know once you're done so that we can move ahead. Don't worry. We still have time.
Done, sir.
Done, sir. Then, well done, sir. We will move ahead now. The next thing, that is one type of charge distribution left, and that becomes your non-conducting sphere. So we will go ahead with non-conducting sphere. Again, electric field would be a repetition, but the more the number of times you repeat one thing, the faster it get, the stronger it binds with your non-conducting sphere. The stronger it will bind with your system and you will not forget it. So if you have a non-conducting sphere, and this is how we are going to draw this non-conducting sphere, so that you get a you get the feeling that this charge which is there inside the sphere is present everywhere in the sphere. It is present in the volume of the sphere, as you can see very clearly. Outside the sphere, we all know the electric field, and in this formula, I have written the electric field in all the possible forms. It has come here. Outside electric field, if you can remember only one form, that is good enough. KQ by R square, good enough. But again, if you can remember in the other forms as well, you never know which form you are going to apply in the question. Potential outside, as you can see, still remains same, whether it is conducting sphere, non-conducting sphere, point charge, everything remains same. The other formulae, whether it's the formula in yellow for electric field or the formula in green for electric potential, are just given in the form of rho. Q is 4 by 3 pi r cube into rho. So you can use different iterations of the same. Anyone know this formula? Exactly same. I'll give you 1 minute to go through this. Remember here in all these questions, we are assuming that the sphere is positively charged and therefore the potential is coming positive. If by chance the sphere would have been negatively charged beta, the potential would come negative. Also remember that potential at infinity is assumed to be zero in all these cases.
Done, sir.
Boys done this time. What about girls?
Done, sir.
Girls are always ready. Good. That was outside the sphere. As you can see, there is literally no difference. The next point that is going to come is the surface of the sphere, and also you can note here that there is absolutely no difference between conducting non-conducting sphere. The formula is exactly carbon copy of each other, but what matters is potential inside. Now remember, in case of your conducting sphere or conducting shell, there was no charge inside that conductor. All the charge was on the surface of the conductor, and therefore potential inside the conductor was same everywhere. But here it is not same because there exists an electric field inside the conductor, and we all know the electric field inside the conductor. This is not the form in which I remember. The black one is the form in which I remember, rho r by 3 epsilon naught. It tells me that it is directly proportional to r. This is the form that I remember. The other one is just a different combination. Because of this, potential inside the sphere is not constant. And a very important result, because this is the result. It might not be coming so much in electrostatics, but this comes in a different chapter in JEE Advanced. In which chapter it comes? Same thing. Might not be required here actually. It comes in a different chapter, and that too in a question of JEE Advanced it comes normally. Where it comes? This blue thing. It comes in a different chapter, not electrostatics. Where it comes? Any idea? Huh? No idea, sir. Get idea, sir. So we don't use idea, we use Vodafone. Not sir, Geo is better. Vodafone and idea have come together, it becomes VI. Yes, in which chapter it comes?
Gravitation, sir.
Gravitation, sir. And I'll try to cover gravitation because maybe in 1 or 2 more classes we will be able to finish your thermo. Heat transfer is also left. Anyways, it comes in gravitation, and that is where we might be using it more than electrostatics. But you have to remember this formula. This is the form in which I remember 1 by 4 pi epsilon naught. I don't remember 1 by 4 pi epsilon naught. I remember it as k cube by 2r cube multiplied by 3r square minus small r square, or x square is the form in which I remember. Now, at the center of the sphere, in the previous case, we had seen that the potential was same as the surface of the sphere. Here it is not, and this is a very important formula. What is the potential at the center of the sphere, and remember this, very important, may not be in electrostatics but in gravitation we will be using it. At the center the potential is 3 by 2 times the potential on the surface, so it is 3 by 2 into k times q by r. 3 by 2 times k q by r, a very important result. All these results so important, they are so lovely and so important that if you can remember them, you can do some really interesting problems, some really interesting problems very quickly. The next thing that you must remember, and it will come as an objective, potential at the center is the highest, followed by the potential on the surface, followed by potential outside. Something has changed. In the case of a conducting sphere potential, there was equipotential and then the potential was going down. Here potential at the center is the highest. Remember, small things make a big difference in your eventual paper and your eventual marks that you are going to get, my dear friends. And here comes the revolutionary graph between the two brothers. One is the electric field brother, the vector brother. One is the simpler one, the scalar brother. And this is how the graph looks like for electric field. Never forget, and we have seen it for other electric fields as well. Graph with a straight line, dig, then ping, 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 ping. Here it is, wee. It goes wee and then dwee. So remember the shape of the graph. This question can come in JEE.
Done, sir.
Everyone, sir?
Yes, sir.
Great, sir. Shall we move ahead in life? Life has to move on.
Yes, sir.
Girls are girls have done. What about boys? Are we there?
Done, sir.
Done, sir. Very well, sir. Then we move ahead in life, sir. And this is the question, sir. This is a question. There are two spheres or two concentric shells, I must say. I can make a question which has 3 shells, 4 shells, 5 shells. Doesn't matter. The concept remains the same. Now, if you remember in the previous case, we had found out the electric field at various points. Now, in this case, instead of electric field, we are going to find out electric potential. Do you remember the question where we found out electric field? Yes or no? Huh? Do we remember? We found out electric field?
Sir.
Yes or no, sir?
Sir.
Yes, sir. Now is the case to find out electric potential. Two concentric. Remember, there could be three as well. The concept remains same. Two concentric two concentric, and these 2 or 3 concentric shell are going to come now from now onwards, because we are going to get into capacitors and this and that and this. So these type of shells are going to come. Two concentric spherical shell of radii R1 and R2. R2 is more than R2 are having uniform distributed charge Q1 and Q2. Find out the potential of point A, which is the center, at the surface of the smaller shell, point B, at the surface of the larger shell, point C, at ding 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 ding. So you have 2 minutes to do this. You don't have to do anything extravagant. Just do simple things and you will land up with your answer. You have 2 minutes to do it. Does but anyone with anything that looks like an answer? No, sir.
There at point A, potential is KQ1 by R1 plus KQ2 by R2.
KQ1 by?
R1 plus KQ2 by R2.
That is correct. Next one.
At point B, KQ1 by R1. It's C KQ2 by R2.
Okay. At point C.
KQ2 by R2.
No K1 will no Q1 will come. No Q1.
KQ1 by R2 plus KQ2 by R2.
That looks good. Correct. So let us first discuss these 3 points, because these 3 points are of prime importance right now. So let us move on to the point 1. Point A. As you can see, this point A, the pink one, this point A lies within both the spheres. So the potential of this point will be same as potential due to the inner shell plus potential due to the outer shell. Remember, potential is a scalar quantity. You can simply add and subtract and stay happy. Don't have to worry about directions. So potential at point A will be K Q1 by R1 plus K Q2 by R2. No prize for guessing this. This is very simple. We move on to point number 2. Point number 2, potential at point B. Point B comes on the surface of first, but still inside the second one. So it becomes K Q1 by R1 plus K Q2 by R2. As you can see, point A and point B are at the same potential. It doesn't matter how many shells you put, potential of any point inside remains same. Do we understand this? Yes or no? Then we move on to the point C. Now the point C, if you can see, is the green point. It is outside shell number 1, but it is on the surface of shell number 2. So for shell number 1, I have to apply the outside formula KQ1 by R2. For shell number 1, I will apply the surface formula KQ2 by R2. Everyone understands this, yes or no? Do we understand this?
Sir.
Now we have inside the shell number 1, between shell number 1 and shell number 2, and outside shell number 2. Can you tell me what is the answer for the fourth one? Fourth one is inside shell number 1. And what will be the answer for inside shell number 1? Potential at any point inside the shell number 1. I will call that point as D. So D point is somewhere here. D point is somewhere here. Inside shell number 1. Yes.
KQ1 by R1 plus KQ2 by R2.
KQ1 by R1 plus KQ2 by R2. What is important to see here is that all of these points, whether you take D or B or A, the potential is same. Remember this. Let us move on to the fifth point. The fifth point is A, B, C, D, E. This E is somewhere in between the first and the second shell. Who is going to tell me the potential of point E?
KQ1 by distance from center to east.
KQ1 by R. The distance is given as R. You can see this. Distance is given as R. KQ1 by R
Plus KQ2 by R2.
plus KQ2 by R2. That is absolutely correct. That takes us to the last one, 6, which is a point EF. F somewhere outside of second shell. What is the potential of that point, VF?
KQ1 by small r plus KQ2 by small r.
KQ1 by small r plus KQ2 by small r. Everyone understand this? Can I have raised hands from everyone in the class that we understand this, sir? And now this is done. First of all, we had found out the electric field. Now we have found out electric potential and we're done. That we understand both of these. Yes or no? No, yes. Oh, this has gone above what I'm saying. Sir, I'm going. Do stay happy. We understand this? Yes or no? Huh?
Yes, sir.
Now this is a question. Oops. Now this is a question which we will do now and probably we'll also use it after some time. This is again a system of two spherical shells. Q1 and Q2 are the charges A and B, or B and A are the radius QB and QA are the charges. B and A are the radii of the two spheres. You have to find what? Find the potential difference between B and A. What is B and A? Between the shell B and shell A. Now, whenever anyone says potential difference between two shells, it is the potential difference between the surface of the two shells. Do we understand this? Yes or no? We understand this? Huh? We understand this?
Yes, sir.
Find out
Sir.
the difference between point B and point A, and then your eyes will open and you will see something fascinating. Let's see who can see that fascination.
A cube by 1 by B minus 1 by A.
K,
Cube, sir.
K QB into
1 by B minus 1 by A.
That is absolutely correct. The answer that you will get, VB minus VA. The answer you are going to get will be like this: KQB into 1 by B minus 1 by A. Yes or no? Did everyone get this answer? Yes or no?
Yes, sir.
How did you get it? You just take this point as B, you just take this point as A, which we have already done in the previous question. You find the potential of point B, you find the potential of point A, and you will see that QA will disappear from the equation. And you only have QB coming in the equation, and that is the big revelation. And what is the big revelation? If you have two concentric spheres, if you have two concentric spheres, if you have two concentric spheres, the potential difference between two concentric spheres only depends on the charge of the inner sphere. That is the big thing that you must remember. Potential difference between two concentric shells only depends on what? Depends on what? Charge on the inner shell. Will you remember this? This is one thing that you should remember. Everyone understand this, or this has gone above our head saying bye bye sir, bye bye, ज़्यादा हो गया sir, bye bye.
Understood, sir.
Okay, I'm trying to devise a question. For that, I'm looking for a diagram. And the good thing is, I am not finding a diagram good enough to become a question. Shameful. Array, I need a diagram. That is all I'm asking for, a diagram. A diagram is what I am asking for, and a diagram is not what I am getting. Shameful. Utter shameful. Can't get a diagram. That's bad. Chalo, then I will have to use this one. It has values written. Can I be smart and take out the without the value? Okay, I can do this. Okay. So here comes the question that I am going to devise. This is a sphere of, since I could not find a negative sphere diagram, so that's why the question is on positive sphere. This is a positive sphere of charge q1 plus q1. I could not find a negative sphere, and radius r1. So this will be plus q2 and radius r2. No prizes for guessing this one. These two spheres, the center of these two spheres are separated by a distance of x from each other. If I call this sphere as sphere number 1 and if I call this sphere as sphere number 2, you have to find the potential difference between the two spheres, V1 minus V2. And your time starts now. Remember, where such a question comes, there must be a condition that must be understood and kept in mind, though they might not give you that condition. What is that condition? Probably would have told you that when I would have done a question on this. What is the condition that must be given, may not be given? That this x is very, very large compared to r1 and r2. Otherwise, nah, chalo. Anyway, that does not change the potential difference, though. That changes the electric field. So. Okay. I wait for your answers. Let's see who gets me the answer. Anyone with anything that looks like an answer? Eh? Feels like one.
Sir,
Yes, bacha?
KQ1 by R1 plus KQ2 by X minus R2 minus KQ2 by R2 minus KQ1 by X minus R2.
Almost correct. I'll give you that one. It's almost correct. It's almost correct. Now remember, what's going to happen is because of these spheres, the charge on the two spheres are actually going to get a bit distorted. It will not remain uniform, no matter how far you keep them. So basically, if you have to find out the potential difference between the two spheres, it's not a good idea to find out the potential difference between this surface and this surface. It's always a good idea to find out potential difference between the center O and the center O of this. As I told you, whatever happens, the potential on the center is same as the potential on the surface. Do we remember this? Yes or no? So let me first find out the potential at the center of the first sphere. What is the potential at the center of the first sphere? K Q1 by R1. This is the potential created by the first sphere plus KQ2 by X. This is the potential at the center of the first sphere. Once you understand the potential at the center of the first sphere, you can now find out the potential at the center of the second sphere. It will be K Q1 by X minus K Q2 by R2. And that, my dear friends, is the answer for the potential difference between the two spheres. We have to find the potential difference between the center of the two spheres. And that is the point that I wanted you to understand.
Sir, plus KQ2 by R2 or minus?
No plus. I took the minus out, so plus. Do we understand this? Huh? It has gone above our head saying bye bye. Sir, I am tired now and I am going. So remember this because we might be needing this, not in this chapter, maybe in the next one, or you might just have a question on this. Note it down, 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 note it down. The more the number of things you note down and the more the number of things that you remember, my dear friends, the better it is for your health.
Done, sir.
By your health, I mean your mental health, not your physical one. Yes, done that.
Yes, sir.
Yes, sir.
Now comes some other configuration. I think I have also given you the electric field due to a semicircular arc, and I told you that same electric field coming in the exam. This is the electric field due to a I gave you a part of a circle. This is a semicircular arc. You have the general formula. Remember, potential at the center of the ring, all the points are equidistant. So even if it is not uniformly distributed, potential will be KQ by R. Do we understand this? No matter how the charge distribution is. Do we understand this? Yes or no? So this could be a uniformly charged ring. For uniformly charged ring, you can find out the electric field directly. For a non-uniformly, you will have to integrate it. That question may not come. But for a non-uniformly charged ring also, the answer will remain same. Do we understand this? Yes or no? No or yes? We remember this?
Yes, sir.
Say na, sir. If you don't say na, then I Dev Sena, and I remember all those Senas. So you please Sena. Don't wait for Dev Sena. Or whatever Sena she was. Noted this down? Huh?
No, sir.
No, sir, then note it down now, sir. Quickly, sir.
Done, sir.
Girls are always fast. Boys who are lazy.
Done, sir.
Well done, sir. Now remember this hemispherical charged body. Hemispherical cap. At the center of this cap, I had given you electric field sigma by 4 epsilon naught. Remember the electric potential also. Sigma r by 2 epsilon naught. There is no point of, there is no time we have that we can waste on deriving this. We can just note the result, use it, and stay happy. At the end of the day, we must stay happy. Nothing else we want. We only want to stay happy. We understand this? Yes or no? No or yes? Huh?
Yes, sir.
Now we come to those cases where I told you But I told you what? Huh? I've told you so many things. But I told you what? No. Before going on to that case, you can note down this case as well. Why should
Done,
I?
sir.
Why should I take a risk? Should not take a risk with anything. Okay. Now we come to some more cases. Just keep noting them then down, and there's no point of me deriving it. It's just integration. I just need to set up the integral, integrate it, get the answer, and stay happy. You can stay happy without it doing all those. So this is a rod. You can see the total charge on the rod is Q. Length of this rod is L. I had given you the formula for electric field of this rod. Yes or no? Huh?
Yes, sir.
This is the formula for electric potential due to this rod. You can also write, my dear friends, what? Q by L as lambda. Q by L as lambda also you can write. Doesn't matter. This is the answer for this potential. Don't have time to derive it. Just note it down. And also there is no point in deriving it. Electric potential due to a rod.
Completed, sir.
Anyone done, sir?
Yes, sir.
I'm not hearing yes, sir, from all of you, sir. All of you, sir. Done, sir.
Done, sir.
Oh, no, sir. Now,
Done, sir.
now remember, in two different cases, I cannot take potential at infinity to be zero. What are those two cases? In which I cannot take the potential of infinity to be zero, and therefore in that case I cannot define the absolute potential because I don't know which point has got what zero potential, because that point is definitely not infinity. Why it is not infinity? Why it is not infinity? Because you have an infinite rod, and since your rod is infinite or infinite line charge, since the line charge is infinite, you cannot say which point will have zero potential because this is also going till infinity. Do we understand this? Yes or no? So in case of this infinite rod, I cannot find out the point whose potential can be taken as infinity. If I call the whatever this is, charge per unit length as charge per unit length as lambda, then I have 2 points, point A, point B. Which point will have higher potential, A or B?
A, sir.
A point will be at a higher potential. Do we understand this? If this is a negative charge rod, then point B will be at a higher potential. In this case, we cannot find out the absolute potential of any point. We can only find out the potential difference between the 2 points. We understand this? Let me call this as RA and let me call this as RB. The potential difference between these 2 points, and we understand that A is at a higher potential and B is at a lower potential, is given by this formula 2k lambda natural log of RB divided by RE. And how do we get this? Probably we'll understand in this class only. This is, in this case, I cannot find out the potential difference between 2 points. I'll have to find out. In this case, I cannot define the absolute potential because infinity even does not have zero potential. So in this case, I can only find out the potential difference between the 2 points. Do we understand this, or this is gone about saying bye bye sir nikal gaya hai to ta na 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 gaya
Done, sir.
Are boys have all of other than woken up. Good. I like boys. Good. That's the spirit. We must not keep sleeping. We must not be found napping. If you are found napping, no, 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 no. Okay. Do we get this?
Yes, sir.
That is the first case in which you cannot find out the potential, absolute potential of any point. Can you guess what is the second case? Can you guess what is the second case? Huh? Oh, for your kind information.
Infinite sheet.
For your kind information, here also you can write the electric field at any point. What was the formula for electric field? Huh? No one knows the formula? Shameful? Shameful act? Shall I wait for you to give me the answer? What is the electric field due to infinite line charge? At any point at a distance r, let us say. Okay, you don't seem to remember. It is 2k lambda by r. Yes or no? Do you remember this? Yes or no?
Yes, sir.
Yeah, thank God, we remember it. We could not speak, but we remembered it. Anyways, that was the first case in which you could not have a point whose potential can be taken as zero. What is the next case in which you cannot have a point whose potential can be taken as zero?
Infinite sheet.
Because I showed it to you, right? Infinite sheet, because again it is infinite. And remember, infinite sheet is the only type of charge distribution that produces uniform electric field. That is the only type of charge distribution that produces uniform electric field. That is the only type of charge distribution that produces uniform electric field. Uniform electric field and uniform electric field. And how much is the electric field? Huh? You do this? What is the electric field? Sir, I don't know, sir. Please don't blame me, sir, for this.
Sigma by 2 epsilon naught, sir.
Anger. Sigma by 2 epsilon naught. Again, I cannot find a point whose potential can be taken as zero, but I can find out. Potential difference between 2 points. For example, if my legendary point A is here, and if my second point B is here, whose potential will be more, bacha? Let us say this distance
Yes, sir.
is A, and this distance is RB. I can find out the potential difference between A and B. Yeah, which point is the higher potential?
A, sir.
Obviously, A, sir. What is the potential difference between A and B? Can anyone tell me? What is the potential difference between A and B? Can anyone tell me? And that is building up slowly for the next thing that we are going to do. These two formulas building up what we are going to do next before one or two questions. After one or two questions. Yes. VA minus VB is equal to, huh?
Sigma by 2 epsilon naught into natural log of RB by RA.
No, natural log. Why should natural log come here? No, my dear friend, natural log does not come here. RB minus RA comes here. Not natural log. Anyways, it was not expected of you to know. So, nothing saying, nothing doing, just moving ahead in life. Do we understand this? Yes or no? No, yes.
Yes, sir.
Are we ready for the question?
Yes, sir.
Well, then, the question arrives, and it will arrive with the Big Bang, just like the Big Bang theory. Question arrives. Question arrives. So these are three plates, my dear friends. This plate, oops, what happened? This plate has a plus Q charge. This plate has a minus Q charge. And this plate has a plus 3Q charge. All the plates have the same area A. The difference between the plates is D. Between this plate and this plate, and between this plate and this plate. If I call this plate as plate number 1, if I call this plate as plate number 2, and if I call this plate as plate number 3, can you find out? Can you find out the potential difference between 1 and 2 and 2 and 3? And how will you do this? Well, just now I told you something here. Can you use this and apply it here? So I'll give you 2 minutes. If anyone can do this, better. Else we will do it after studying something else. You have 2 minutes to show me your talents.
Sir,
Yes.
2Q by D, sir.
2
Q by D.
2Q by D. Dimensionally, 2Q by D. No A is coming. Okay. Well tried. Well tried. I was not expecting that you will get it, but well tried. At least you tried. Chalo. Anyone has done this? Huh? Anyone with any other answer? The charge on the plates is given, area of the plates is given, distance between the plates is given. Can anyone tell me what is the potential difference between the two plates? Okay, forget about potential difference. Can you tell me which plate will be at higher potential between 1 and 2? Which will be at a higher potential? Between 1, huh?
1.
1, chalo. Which will be at a higher potential compared to 3 and 1? 3 and 2, not 1. Between 3 and 2, which one will be at a higher potential? Huh? No idea? Get idea. We have Vodafone.
3, sir.
Hmm?
3, sir.
3, yes. So between 1 and 2, 1 is at a higher potential compared to 2, and between 3 and 2, 3 is at a higher potential compared to 2. What is the potential difference between the two? We will come back to this question maybe in today's class only, because we are going to write the next heading, and the next heading is known as what? Relation between electric field and electric potential. That is the next heading that we are going to do. Relation between E and delta V. Now, the first and the most important thing to understand here is one is a vector quantity and the other, gentleman, is a scalar quantity. How can a vector relate with scalar? One is a vector, other one is a scalar. Huh? How can a vector relate to a scalar? How can a vector relate to a scalar? Anyone has heard this? Vector getting related to a scalar? It's like a vegetable getting related to an fruit.
Dot product.
Dot product. Yes. Our old friend dot product comes into the picture. And how does this dot product come into the picture? And I will take you back, 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 so much back. So back, so much back. Back, 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 back. Here. Here, and I think we have already discussed this potential difference between A and B can be VA minus VB will be nothing but UA minus UB divided by Q. Yes or no? UA minus UB is work done divided by Q. F dot dr divided by Q. F by Q becomes your electric field, and this is the revolutionary what? Relation between electric potential and electric field, which I have already told you. Now we'll just go back to it again and write it again, because this is the time then we are going to move ahead with questions based on this relation between electric field and electric potential. So I can write the first statement like this: dV, change in potential, is minus E dot dl or dr, doesn't matter how I write it. I just want to write it as line integral, and that's why I'm using L. dV is minus E dot dl. Change in potential is negative of the dot product of E dot dl. Or I can write dV ka integral will be equal to negative integral of E dot dl. If I do the integration from A to B, this is integrated from A to B. On the left hand side, I have VB minus V, and on the right hand side, I have a negative. So I can write VA minus VB, and I can take the negative sign out, is integral of E dot dl A2. Do we understand how I've written this? Yes or no? Yes or no?
Yes, sir.
Now, if you look at this thing, this is known as the line integral. Have you heard something like this before? This is known as the line integral. Have you heard something like this before?
No, sir.
I heard some of these YouTubers who were giving this funda. I told you, trick of scoring 200 marks in physics or maths. Whenever there is a zero, always mark zero. That is the trick. That is a smart trick. So on similar line, there is a trick. Whenever I ask you, have you heard this before? The only answer you say is yes, because then only I ask you. Right? So have you heard this before? The answer is yes. Now the next question would be, where would you heard? Where have you heard? Then you can say, sir, I forgot. But whenever I ask, have you heard it? Definitely I would have said something that where I have used it. So whenever you get zero, mark zero. That is a very hardcore trick. And sometimes it works as well. So whenever you see zero, mark zero. Quick tricks to score 180 marks in physics in NEET or 100 marks in physics in JEE. Wherever you say zero, mark zero. Do not do even akkar vakkar bambe bo. Even akkar vakkar bambe bo may fail, but whenever you see zero, you mark zero. Because zero is always an answer. Remember that. Whenever you see zero, mark zero. Best trick that I have ever heard in my life. Whenever you see zero, mark zero. Anyways, meanwhile I was passing time. I was just going back in time. See, I've got a time machine that I can use to go back in time and present to you the past. And this is a glorious past. We had seen something like this. Flux through a closed surface. And here it was E dot ds. And then I told you this thing is known as the surface integral of electric field. This is integral of surface over of an electric field. What we are dealing now is the line integral of electric field. Surface integral of electric field gives you flux. The line integral of electric field gives you potential difference. And that is what you should remember. The line integral of electric field gives you the potential difference. Surface integral gives you flux. Line integral gives you the potential difference. Line integral of electric field gives you the potential difference. Do we understand this? Now,
Yes, sir.
if I put a gola over the line integral and I write line integral over this gola, what will be the answer for this line integral? This gola means I start from one point and I come back to the same point. I start from one point and I come back to the same point. And we have been doing this one point and the same point in thermodynamics as well. I start from the one point and come back to the same point. Then what happens to this gola, this integral? This gola becomes, I told you, whenever there is 0, mark 0. So here the answer is 0. Whenever there is 0, mark 0. The quickest trick that anyone could have ever said. Wherever there is 0, mark 0. So line integral of electric field over a closed surface is going to be 0 because this is a conservative field. Work done in a closed loop is 0. Work done in a closed loop is 0. Change in energy in a closed loop is 0. Change in potential in a closed loop is 0, and therefore all these are zeros. So wherever you see 0, you mark 0. So that is what you need to remember. The line integral of electric field over a closed loop is 0 because that means you are starting from that point and going back on the same point. Potential does not change. There is no work done. There is no change in internal. There is no change in energy. There is no change in potential. Do we understand this? It has gone above our head saying, "Sir, ये तो चले ही गया अभी." We tried a
Yes,
lot,
sir.
but it has gone above our heads. So line integral of electric field. So if you want to find out the potential difference between 2 points, what do? You find out the electric field. Take the dot product. Put the sum. Stay happy. Do we understand this? Or above our heads, it has gone.
Understood. Understood, sir.
Pakka?
Yes, sir.
That is how you will get the potential difference between the 2 points. And what better example than this one? The electric field due to a sheet, infinite sheet, is sigma by 2 epsilon naught. And this is the only type of charge distribution that produces uniform field. Remember it. Electric field due to a sheet is sigma by 2 epsilon naught. What will be the potential difference between 2 points whose distance from the sheet is RA and RB? And how will you find it out? How will you find it out? And this is the exact way it has been found out. I'll give you 2 minutes to set up the integral, get the answer, and stay happy. At the end of the day, we all must stay happy. Everyone could set up the integral. So how do I set up the integral? Electric field is already known to me. So I can straight away write here VA minus VB will be integral of electric field is sigma by 2 epsilon naught into I take small distance dx, E dot dx. Electric field and dx are in the same direction. So their dot product becomes 1. I integrate this from where to where? From point A to point B. The distance of point A is RA. The distance of point B is RB. You integrate this, definite integral. You put the limits and you end up with that answer in the previous case. Do we understand this?
Yes, sir.
Everyone got this?
Yes, sir.
Pakka, sir?
Pakka, sir.
Everyone has written this integral in the sheet, whatever their space was. Everyone has noted down?
Yes, sir.
Come back to the previous question, where we had electric field due to an infinite line charge. Now if you have to find the potential difference between point A and B, what do? You again set up the integral. VA minus VB will be equal to integral of electric field is 2k lambda by r multiplied by dx, but you are using r, so multiplied by dr. The angle between E and dr is 0. You just put the integral from RA to RB and you land up with the result that was there. Do we understand this, or this has gone above our head saying bye 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 bye?
Understand, sir.
So this is how electric field or how electric potential difference can be found out from electric field in any case. In fact, in all of these cases that we have written, you can find out electric field from the same principle. Without using potential, you can find out electric potential from electric field. Do we understand this? Here also you can do it in this way. Any case, here also, it is exactly done in this way. That is why you got this potential. Do we get this? Yes or no?
Sir,
Relation between electric field and what?
potential difference.
Electric field and potential difference. So I have given you this, and I will create a hypothetical field, and I will, let me see if I have any question here that I can cut, copy and paste. That would save some time. Otherwise, I will have to create my own creation. 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 I will have to create my own creation because I can't find a question. So this is the question that I am creating. Do it fast. Don't have enough time. So question number 1. Electric field. Let me not use vector now. Let me just. Electric field at any space is given as E naught into x. E naught into x. Find the potential difference between 2 points at x is equal to 1 and x is equal to 3. So do it fast. You have exactly 2 minutes to do the question, get the answer and stay happy.
Sir, for E naught.
Not, sir.
Well done. I have a very quick answer for E naught. So how you get to do this? So simply what I need to do, I need to set up the integral
Relation
v1.
of E naught x into dx from 1 to 3.
So E naught x dx from 1 to 3, and it is simply E naught x square by 2, and you put the limit from 1 to 3 and you end up with your answer. Do we understand this? Yes or no?
Sir,
Sir.
Okay. Now question may come like this, or question may be electric field might be given in the vector form. So change in potential from electric field in vector form. How do you do this? Remember, don't get scared. You just need to take a deep breath and do it. So the question would be of this nature. Electric field will be given something like this: EXI hat plus EYJ hat. Now remember, whatever we are doing is doing for a number of things together. Now, in place of electric field, this could be force. and you are supposed to find out the work done. Same method. This could be conservative field, and you are supposed to find out the change in electrostatic or gravitational energy. Same concept, same principle, same working procedure. So let us say dr is written as dx I hat plus dy j hat plus dz k hat. Now, how do you find out the potential difference between 2 points? If I have to find out VA minus VB, what I'm going to do is I'm going to take the dot product. You must understand that once you take the dot product, this gets multiplied by this gets multiplied by this, and this gentleman gets multiplied by this, and then you have to integrate it. So basically what you got to integrate is integral of EX dx plus EY dy plus EZ dz. Do we understand this? Now
Yes, sir.
this can be applied whether the electric field is uniform. It can be applied when the electric field is non-uniform. It can apply for any type of electric field anywhere in the universe. So this way you can find out electric potential difference from electric field. You have to integrate it from the coordinates of point A to the coordinates of point B. We understand this? Have you noted it down?
Yes, sir.
Then I will give you a question. An electric field at any point in space is given by 2xi minus yj plus 4k. Find the potential difference between A and B. Coordinates of point A are 1, 1, 2. Coordinates of point B are minus 1, 2, 1. You have to find the potential difference between these 2 points. Electric field is given to you in this fashion. Yes, anyone with an answer?
Yes, 1/2, sir.
Okay, I think that must be correct. I'm not concerned about the values that you get. I'm more concerned about whether you are doing it correctly or not. And I'll set up the integral, and I hope you can do it after that. So I have to find VA minus VB. So what do? I just take the integral of EX into DX. So it is 2x dx. I can take it outside of the main integral, and x has to be integrated from 1 to minus 1 minus y dy, that has to be integrated from initial point 1 to final point 2 plus 4 times integral of dz. Z has to be integrated from 2 to 1. Have you set up this integral like this? Yes or no?
Yes, sir.
You can just, you know how to integrate this. You can just integrate it, get the values, get the answer, and stay happy. Everyone can do this. Yes or no?
Yes, sir.
Okay, so I leave it here, and I hope you can get the answer from this one. Shall we move ahead?
Yes, sir.
Okay. This was to find out electric field, to find out electric potential difference from electric field in a general case when it is given in the form of electric field vector. Now let us break it down into simpler cases, and we are expecting questions on these simpler cases, and then we'll come across what happens. Now, if electric field is uniform, and most of the cases you might be encountering where electric field is uniform. Now, if electric field is uniform, what will happen if its electric field is uniform? Now, we have seen that VA minus VB is nothing but integral from A to B E dot dr, yes or no? Now, if electric field is uniform, this integral simply becomes E dot delta R, yes or no? If electric field is uniform, this becomes E into E dot delta R, or I can write it as E into delta R into cos theta, yes or no?
Yes, sir.
That means now VA minus VB, I can now understand VA minus VB is positive if theta is 0. We understand this? Or I can say in the direction of electric field, or I can say in the direction of electric field, potential falls. Or I can say electric field always goes from a point of, electric field is directed from a point of higher potential to a point of lower potential. Do we understand this?
Yes, sir.
Okay. VA minus VB will be negative if theta is obtuse. If we are moving opposite to the direction of electric field, if we are moving opposite to the direction of electric field, if we are moving opposite to the direction of electric field, potential will rise. Do we understand this?
Yes, sir.
Okay. If theta is 0, if theta is 90 degrees, and this is a very important case, then your
0, sir.
point A becomes potential at point B, or we can say potential does not change potential does not change if what? Potential does not change if we move perpendicular to the direction of electric field. That is, if E is perpendicular to your displacement, then the change in potential is 0. Potential does not change. Potential does not change in the direction perpendicular to the electric field. Do we understand this, everyone?
Yes, sir.
These are the important things that you must understand. Now, also remember Potential difference does not depend on path. Potential difference between 2 points. It's a conservative field. It does not depend on path. It's a very important thing that you must understand. Give you 1 minute to note it down. Then I can give you some small questions which are more likely to come in the examination hall. Give you those questions. Please note down everything.
Done, sir.
Girls, are we done?
Sir.
Okay.
Done, sir. Done, sir.
Okay, so here is a question that I have written for you. You have to find the potential difference between point A and B, A and C, D, E and G. What is the potential difference between these 2 points? Electric field is given, some distances are given. Can you find out the answer? We have 2 minutes. Yes, anyone got any answer? Or shall I do it?
Next one, 10, sir.
VA minus VB, how much? Plus 10 or minus 10?
It's 10, sir.
Plus 10, sir. That is absolutely correct. What about A and C?
Is equal to VC, sir.
Uh, between A and C, what is the potential difference?
Difference, sir.
Answer is 0. When you are going from A to C, I am moving perpendicular. So in fact, this point, this point, this point, and this point, they are at the same potential because they are perpendicular to the electric field. Do we understand this?
Sir.
In fact, this surface is known as equipotential surface, which we will discuss in the next class tomorrow. This is an equipotential surface. Okay, what is VD minus VF? Which point is at
4,
a higher
sir.
potential?
4.
It is plus 4. What is
1
VE
plus 8.
minus
Plus 8.
plus 8? Everyone understands this, how it is done?
Sir.
Yes or no? No, yes.
Sir.
Okay. Shall we move on to the next question then, everyone? Everybody noted this down.
Noted, sir.
Okay, then this is the next question that I am trying to frame. Potential of point A is given as 3 volts. You have to find the potential of point B, C, D, and E. You have 2 minutes to do this. Yes, anyone?
1 minus 3, sir.
Okay, out of B and A, which one will be at a higher potential, A or B?
Yes, sir.
Out of B and A, which one is at a higher potential, A or B?
Yes, sir.
B, sir. Please remember that, sir. Don't forget it, sir. Electric field always go from higher to lower. So I can write VB minus VA will be equal to 2 multiplied by 3. Yes or no?
Sir.
And VA is 3 volts. So the value of VB will be plus 9 volt. Do we understand this? Not minus 3. We get this or no?
Sir.
Everyone understands this? Electric field always goes from a point of higher to lower, not lower to higher. What about C? Which point is at a higher potential? C or A? Which one is at higher potential? All these are equipotential points. Do we understand this? Yes or no? All these points here are equipotential. Do we understand this?
Yes, sir.
Okay. So which one is at a higher potential? C or A?
C, sir.
How can A be at higher potential, yaar? Electric field lines go from higher to lower. They are coming from C. So how can A be at a higher potential, bhai?
I said C only, sir.
Okay, you said C only, sir. Then something wrong with my ear, sir. So VC minus VA will be equal to 1 multiplied by 2. So your VC will become 3 plus 2, 5 volt plus 5. Yes or no? We understand this?
Yes, sir. Understood, sir.
Okay. Which point is a higher potential, D or A?
Yes, sir.
VD minus VA will be 2 into 2, 4. So VD becomes plus 7 volt. Which point is a higher potential, A or E?
Yes, sir.
A, sir. So VA minus VE will be 3 into 1. 3 into 1? 2 into 1. Why am I multiplying 3? 2 into 1. So VE will be 1 volt. Do we understand this? So
Sir.
this is how you can find out electric potential difference from electric field. In the next class, we will do one more question on this and then try to find out the reverse of it. From electric potential difference, can you find out the electric field? So we will do that in the next class. Till then, take care. Have a nice day. God bless all of you. I hope you have understood what we have done in the class today. Okay,
Yes, sir.
till then. Bye bye, beta.
Bye, sir.
God bless you.